Okay. What we're going to do tonight is we're going to look at the derivative, because from now until the end of the unit, pretty much all the time left is about looking at calculus. All we really need to be able to do is the stock standard processes in differential calculus and integral calculus, so that when you go on to the next unit, which is specifically about calculus, you've sort of got all of those basic processes and techniques well learnt, so that when you get there, you're well prepared to do so. So what we're going to do in this unit, in this session, is these things. We're going to go back to what we did in the last week and talk about limits initially, because the idea of limits is actually where differential calculus originally came from when it was developed by Newton and Leibniz way back a couple hundred years ago. What we're going to do is look at the gradient of a function. We'll just look at a straight line initially and recall what a gradient is. We're then going to do it for a function that isn't a straight line and look at how you have to think about approach the problem from a limits perspective. Then we're going to look at how you use the limit approach to get a derivative. And then we'll start at the end of the session on the first couple of basic differentiation rules. As you'll find when we get there, if you had to do it from first principles all the time, you'd give it up quickly enough, because it's a fairly painful process. Now, let's recall this one just from when, this was from the session last week. We remember that when we have a function, in this case the function is 3 over x minus 6, and the red line's the graph, we represent limits using this technique. So we read that as the limit, as x approaches 6, of 3 over x minus 6. Now what we're posing here is we can look at the idea of a limit as approaching the value of 6, which is, it's x equals 6, which is right there. No, it's not, right there. We can come in from the left, from below 6. If we do that, the graph is actually going down here, so it's heading off to negative infinity. We can come in from the right above 6, in which case the graph is going up that way. In each case, the reason for that is because that has a different sign depending on which side of 6 you're actually on. If that is just a bit above 6, a number just above 6 minus 6 is positive, so the whole thing is really big but positive. If that is 6 but just a little bit below, on this side like 5.99999, x minus 6 is then negative, so that whole thing then becomes a really big negative number. That's why the graph actually goes off to negative infinity instead of positive. So this idea of limits is important, because it's this idea that we've got this place and we're getting closer and closer and closer to it, that we never quite get there. So that's the way, that's where we sort of got to. Whether this exists or not isn't so important this week, but the idea of how a limit works is. Now, let's just remind ourselves of another piece of underlying mathematics that you need to work from to get this idea of the derivative. Let's take something like, you have 2 points, 1, 1 and 3, 5, and we want to work out the gradient of the line between those 2 points. We recall that, and there they are, we recall that the way we think of this as that the gradient between any 2 points is rise over run. So I have my line between the 2 points, and I have my rise, which in this case is going from there to there. So it's, and the rise is always in the up and down direction, so that's the y coordinates, which are these two. So the rise goes from y equals 1 to y equals 5, which is a rise of 4. The run, on the other hand, which is in the x direction across here, we're going from x equals 1 to x equals 3, so the run is 2. Right? No big deal, we've seen that from way back. We recall now that therefore the gradient, which is rise over run, is 4 over 2, which is 2. Now, what we think of when we think of a gradient is, it's for every one along to the right I go on the page, it's the number up and down I have, or up or down I have to go. So if I have a gradient of 2, it means 1 across and 2 up. If it'd been negative 2, it would be 1 across and 2 down. So that's all of our work from coordinate geometry. Now, working out a derivative is no big, a gradient is no big deal if you've got 2 points and what connects the 2 points is a straight line. The gradient on every point on the line is exactly the same because the steepness of the line never changes. But what happens if I have something like this? This is the gradient. The green line is the graph for y equals x squared. As you're aware, that's a parabola. Let's think about the gradient of the line. If I look down here at 0, x equals 0, at that point the gradient is actually flat, it's horizontal. So it has no gradient, it's a gradient of 0. It has no steepness if you want to think of it that way. If I go back to that side of 0, the line goes down the page, so therefore the gradient on that side is negative, and on the other side of 0, over there, the gradient is positive. So when you have something that is not a nice flat straight line, which has a constant gradient, something like this has an ever-changing gradient. So what we need to do is to have a technique that allows us to work out the gradient of curves and functions that are not nice straight lines. And that's what the derivative allows us to do. That is why whenever you get from a fundamental simple problem which involves straight lines to anything more complicated, it involves calculus. And that's why calculus underpins a large amount of the work that you do in any advanced mathematics. Because very few things in the real world are nice straight lines or linear relationships. So what we're going to do is have a look at how the idea of how I can look at this and work out a gradient of the curve, but basing it in the mathematics of the gradient of a straight line between 2 points, because that's where it was. That's the way it was actually worked out by Newton and Leibniz. So let's think about for a second, how do I get the gradient of this function y equals x squared actually at x equals 2 at that point right there, the orange one? If the gradient at that point is in fact a line which is the tangent, hang on, turn the light on. All right, can you get it? Sorry about that. If you think for a second about the line that joins the 2 points, let's look at the line from 1, 1 to 2, 4. As you can see, the line, particularly in the middle here, there's a difference between the line that joins those 2 points and the function. The function isn't a straight line, it's a curve. So therefore, what we have to try and do, if I'm going to represent this with a straight line, the straight line that would represent the curve at 2, 4 is actually called the tangent to the curve. It just touches the curve in one place. The problem with that is that if it just touches it in one place, you haven't got 2 points on the curve itself that you can work with. You've only got one. So what we do is we consider 2 points on the curve, but we try to get them really, really close together. And if they're sufficiently close together, the gradient of the curve, the tangent of the curve, will have essentially the same gradient as the gradient of the line that joins the 2 points on the curve, which are really close together. And that's the thinking behind where the derivative is actually coming from. Notice here, I've actually drawn the line which is tangential to the curve at 2, 4. Notice that they do not have the same gradient. If I take that point there, this one, and I move it around the line, the curve, up, and as I get closer and closer to 2, 4, the lines virtually become the same line. So that's the thinking that we're going to apply. Now, this is the definition of the derivative using limits thinking and notation. What we're going to do is have a look at the different parts of the limit equation and work out where it comes from in relation to what we were just talking about having a point and coming up the curve and getting closer to it. Now, what we'll do, this is again the curve y equals x squared. What I've done is I've put 2 points on the curve, and we're going to move the red dot closer up to the blue dot just to see what happens. Now, first of all, consider the function at the red dot it's just some random point. So if I start with the function there, which is f of x, if I move to the right from there, that distance, and call that distance h, what I've done is moved out that distance h, but the function has gone up to there. So if I'm going to represent this with the notation, what I end up with, that point there has a y coordinate of f of x plus h, because that is the x coordinate for that point is x plus h, because it's the original one plus h. The y coordinate is now the value of the function at x plus h, which is f of x plus h. What that means is, when I look at that triangle, that distance there, the horizontal run is h. That distance there, which is the vertical rise, it's gone from the value it was originally, which is f of x, up to f of x plus h. It's risen the difference between those two things. What you'll end up with is that. So if we now look at this equation, and the reason we're just using f of x and x plus h is because they're just any 2 random points, they're just 2 points on the function. They could be any 2, and that triangle would result. What I want to do now is consider how I get that point and move it up the function right up there and get it as close as I can to the blue one. Because remember, as they get closer and closer together, the straight line between them gets closer and closer in gradient to the gradient of the curve itself, the green curve. Well, hang on, I'll back up. I couldn't see that behind my thing. So if I now think just gradient is rise over run, so for that triangle, the rise of the straight line is that distance, which is f of x plus h minus f of x, the difference between the y's, over the run, which is that distance, which is h. Yes, that's actually what we're going to do. We haven't got that far yet. What we're doing at the moment is just considering the triangle in its current state, where they're a nice long way apart so we can see them. At the moment, the way it's drawn, we can see that the line is not close to the curve at all. So what we have to do is, as that point comes up along that way, that h value there gets shorter and shorter and shorter. So what we're going to consider is the limit of what happens in the limit as h actually approaches 0. And that's the bit at the front. What we have to add to it, so therefore, is we take the original calculation of the gradient of the line between 2 fixed points on the curve, and then we add at the front, get them closer and closer together so that h in the limit as h gets to 0. So that calculation will approximate the line that is the tangent to the curve, which is what we're actually after. So what we have there is the definition of the derivative to a function. And that was developed by Newton and Leibniz back a couple 200-300 years ago. Pretty smart fellows, if I do say so myself. Now, that's all well and good. Let's consider what happens, though, in practice, how we actually might use this to work out what the derivative of something is using this limit approach. Let's take something like this. First thing we'll do is I'll go through the steps. I'll just show you how it works first and explain what each of the steps are in the process. So if you get one of these in an exam, if it just said that in an exam, you would do it any old way you like. It doesn't require you to use first principles. If it said find f dash f of x equals whatever, using first principles or using the limit definition, you have to do it the way you're going to see it now. But you only do it this way if you're explicitly told to do so, and you'll see why in a second. Now, first of all, the first thing we do there is we write down the limit definition of the derivative exactly without any change at all, because that's the thing we're going to base it upon. What we've done is, in this first step that I've shown you, notice that f of x plus h is all of this front bit. What f of x plus h means when you work it out is you have to take f of x, and wherever you see x, you have to replace x with x plus h. So the original f of x was 3x squared plus 2x minus 1. So it now becomes 3x plus h squared plus 2x plus h minus 1. So wherever we've seen x, there and there, we've replaced it with x plus h. The next thing we have is we subtract f of x at the right-hand end here. Now, subtracting f of x just means I have to take all of that and subtract it. To subtract it, though, I have to make sure that I put it in a bracket. If you leave the brackets off, it doesn't work, because you only then subtract the first term, you don't subtract the whole thing. So what we have, right, make sure the f of x goes in a bracket. So what we have, if we just back up a bit, there, that second line is a stock standard one. It looks very complicated, and it is when you do these problems, it's very easy to make a mistake, because there's a lot of algebra and adding things to it, whole heap of terms together. If you more often than not, the errors that you make, you drop a sign in the second half, or you square, when you square something like x plus h all squared, you get it wrong. Let's do something silly. In an exam, so long as your process is essentially correct, you'll still go really well on the question. Now let's get back to where we were. Now that's the next line. What we now have here, we have to go from where we were there and simplify it, and we expand it and simplify it. So the first thing we do is we get rid of the x plus h squared, that bit there. We're multiplying out x plus h all squared, and it becomes x squared plus 2xh plus h squared. The second term is expanded, so we take that term and expand the brackets, it becomes 2x plus 2h. The minus 1, we don't do anything with that. And the last bit is we distribute that minus across that whole second half. And that's always done. This line here always involves taking whatever that function is and making minus all of it. So you have to change the sign on every term. So the 3x squared becomes negative, the 2x becomes negative, and the 1 becomes positive, because originally it was minus 1, and minus of minus 1 becomes positive 1. Then what we do is we expand a little bit more, because we've still got a bracket out the front. So we expand again, so it becomes 3x squared plus 6xh plus 3h squared. Now we've got all this junk up the top in the numerator. You will always be able to cancel out some of the terms. What I've done there, you see the 3x squareds cancel, the 2x cancels, and the 1 cancels. Notice that the things that cancel are the terms of the original function, and that should always happen. If you're at this line and you can't cancel all the terms of the original function, you've mucked it up. So what you do before you go on any further is go back and just check all your algebra up to that point. The things to look for, of course, as I said earlier, things where you've done a product of a bracket, expanding brackets, and that negative. More often than not, it's dropping a sign on the negative where your errors arise from. So now what we have, we've cancelled out a whole heap of terms, and we reduce the problem now down to that. What we notice here is that we have a problem, and we've had this from the start, from the very first line. The problem is, if you have a look at that, h is going to 0. Now, because h is in the denominator, what that means is that h going to 0, it appears on first look that that function, that thing that we're trying to work out, that limit should be maybe well be undefined, because if h goes to 0, the denominator is 0, we can't work it out. But you will recall from our work last week that when we get to this point, what we look for is the capacity to factorise the numerator. If I can cancel that h, that will get rid of the problem with the whole thing being undefined, and I'll actually be able to work out the limit. 2xh. Okay. Amelia's asked where that term there comes from. Now, what that one is, if I take that there, x plus h, I'll try and write it as best I can, but as usual, this doesn't work very well. X plus h, that's, might as well use my pencil, squared is the same as x plus h by x plus h. That's what x plus h all squared means. What you then do is expand that as two brackets. Yeah, so you then FOIL that. The fronts give you the x squared, the backs give you the h squared, but the outsides and the insides, they each give you an xh, and when you put them together, you get 2xh. Right? You can do that in more steps if you need to, but the thing is with these, I would bet my last dollar that the one you get in any exam situation is going to be a polynomial like this. And therefore, you'll be doing this a lot. Once you've done it, once you do a few of these, this was always a part of it. So you get pretty good at going from there to there all in one big jump. If you're trying to do it with a cube, I would actually work it out on the side of my page, how the expansion for the cube, and then I'd shove it into the next line. So I go straight from there to there. I do that in one step, and I have my working out here to the right. The reason I do that is because if you do it all in here, it sort of throws everything in together, and it gets really messy, and it gets really easy to make a mistake. So that's good, Amelia. I'm glad you see where that comes from. I'll just get rid of that. Whoa, that didn't work so well. I'll just get rid of that bit so we can continue on. Now, what we then do, and going back to where we were, the problem we had was, with the h, while that h stays in the denominator, the whole thing is undefined. So what we now notice is that every term in this numerator has an h in it. So I can take h out the front and factorise the numerator, and I get left with 6x plus 3h, because I'll remove one of the h's, plus 2. The h's then cancel, and I've removed the problem of this thing being undefined. Now keep in mind when you do this line, the top must factorise, because so long as the h is in the denominator, the thing's undefined and it just won't work. So unless your function doesn't have a derivative, and I can guarantee in an exam you won't get one that is like that, it will have a derivative, and it's not going to be very hard, because otherwise, as you can see, it's a fairly time-consuming process. It's going to be relatively simple. So if you can't factorise that numerator, it means you made a blue somewhere. You've dropped the term or something. So now that we can have cancelled out the h's, what I can now do is I get that. Notice here, h is going to 0, but we've just got a nice simple term. Some of them will have h in them. Some of them will not. Anything with an h in it is just 0, because it's just a simple term, and it's the limit is h goes to 0. So the value of that part is just 0. So that just disappears, and we get anything without an h in it gets left behind, because the limit as h goes to 0 of 6x is just 6x, because it doesn't have an h in it, so you've got h going to 0 doesn't make any difference. So what you end up with is that. So if you look now back at what we started with, that function, 3x squared plus 2x minus 1, the derivative of it is that function, 6x plus 2. A simple function, a polynomial function with a polynomial result, which is an order, which is 1 less. And that's going to keep that in mind, because it's actually going to come up again at the end of the session tonight. Notice that even though the function is simple, it's a parabola, the process by first principles to get from the function to its derivative is a fairly long process. None of it's particularly difficult, but there's a lot of work involved in the algebra, and then you have that limit problem at the end. So it's no big deal. It's just easy to make a mistake. Now, let's have a look. Let's go back over this again in terms of the key steps that we have in applying this technique. Step number 1, when you do these problems, it'll say, find the derivative of this function from first principles or using limit definition, one or the other. First thing to do is just write down the definition. So f dash x equals, the limit as h goes to 0, f of x plus h minus f of x over h. You just got to learn that. It's like the quadratic formula, just learn it. You don't have to justify where it comes from, you just learn it. So write down the limit definition as the first line of your solution. Then you'll recall that we have to then go f of x plus h. So that front term becomes the function that we're trying to get the derivative of, but we replace x with x plus h anywhere we see it. So that's the front part. We then replace the back part with what f of x actually is, with the function that we're trying to get the derivative of. But we must importantly remember the whole thing goes in a bracket because we're subtracting it, and that subtraction sign has to get distributed across whatever the function is, the totality of it. The next step, once we've done that substitution for f of x plus h and f of x in the formula, we then just do an expansion and a simplification. We expand out the front term, because it'll be guaranteed it'll be a polynomial, so you'll have to square and maybe cube something. Then you distribute the negative across the f of x. Then we just slog it out with the algebra, simplify the terms, cancel it down, and we remember whatever the original function was must all cancel out of that work when we do it. If it doesn't all cancel out, you've made some sort of arithmetic or algebra mistake somewhere. Once we've simplified it down, the next step was to factorise the numerator so we can get rid of the h in the denominator. And h will always come out if you've done it correctly. Once you've factorised it, you can then cancel the h out and then finish it off by applying the limit, because anything that's left that's got an h in it just disappears because h is going to 0. So what's actually left behind as the answer is anything without an h. So, and they were the steps that we went through. Is everyone happy with that approach? It works the same every time. It's never different. There's no trick to it. What you've got to do to be able to do this well and be able to produce it in an exam and not get stuck in it and take too long is you just do a whole heap of them. Just do it with polynomials and just make sure you've got those steps really well oiled so that when you just sit down, you can start and you just go blur and follow it through the same every time, because it never changes. Is everyone happy with that? Big thumb up. Proving good. Kale, you okay? Good. Let's move on. There you go. Have a crack at it. See if you can use the steps that we've got in those things to just that nice simple function, f of x equals x squared, and see if you can work out what the derivative Reece, that's too quick. You've got to do it from first principles. We haven't got the power rule yet. See if you can get through. Yeah, the answer, as Reece has pointed out, the answer is 2x. See if you can get from there to 2x using the limit definition. Just take a couple of minutes, then I'll show you the solution. We'll see if we get the same stuff. Give me a tick or a thumbs up, something when you're done, and so I know when people are finished. Good. Reece is done. Okay, what I'll do, Amelia, I'll go back and show you the final solution for the other one. There we go. Essentially, it works in exactly the same way as this one. Although, obviously, the algebra is a bit simpler because it's just x squared instead of that one. See if that helps. So what I'll do is I'll go back to it and we'll work through it step at a time, highlighting what each of the steps are, compare it to what you've done, and make sure that it marries up to how it's going. Joshua's just typing something, I'll just let that happen. Somehow I took my own photograph, that's all right. Yep. What we'll do, I'll go through and we'll just make sure that each step you've done marries up with what I've got. So as we said before, step 1, write down the formula, because that's the first mark. If you write that down, you're off to a good start. We remember from our steps, step number 1 is replace that bit there first. So the function, the original function was x squared. Everywhere we see an x, we have to replace it with x plus h, which means it's now be x plus h squared. The back half of the function, which is this bit, of the derivative I should say, becomes minus f of x. So that's the minus of whatever it is the function is, which is x squared. So it becomes minus x squared over h. So that bit there is that, and that bit there is that. Notice even when I've just got a nice simple thing like x squared as my function, I still stick it in a bracket at the back. I highly recommend you get in that habit, because if you don't, if you make it means that you'll always use a consistent approach, and you will make sure that you put that negative in the middle there, that thing there, and you will distribute it across the bracket. It's just a way to make sure you remember. So the next step, once we've done the replacement, we remember that the next step is to take that numerator, expand it first if it's necessary, and then simplify. So the next step, expand and simplify. So we have to square x plus h all squared, which is x plus h times x plus h. So if you do write it like that over at the side and FOIL it, you will get that. So that bit there is x plus h all squared, and that bit is that at the back with the minus on it. That step is always the same. That back half, you just put the negative across all the function at the back. Is everyone right so far? Yep, good. No other dissenters? Good, I'll continue on. Good. So, we remember that the next thing we do is we simplify, and when we simplify, whatever was the original function, every term in it must be able to be cancelled out of that numerator. Notice that we have the original function, which is x squared, and there's a positive x squared, and there's a negative x squared. So they can cancel out. And what you get left with is just 2xh h plus h squared all over h. We know the next step is that that numerator must be able to be factorised. You must be able to take an h out of it, because while we've got this h in the bottom, that thing won't work because the h is going to 0, which makes it infinite. So we now factorise the numerator by taking out the h, cancel the h's there, and it just leaves 2x plus h. And at that line there, we apply the limit. We don't do the limit until we've gone through that whole process. And we know that any term with an h in it, like that one there, is 0. Any term without an h, like that one there, which is 2x, just stays exactly the way it is, and we drop the limit off. So the answer becomes 2x. Got it. Well done, Joshua. Is everyone happy with that? Yep. Good. Okay. Let's have another one. Same deal. There it is. Have a crack at doing that using the limit definition. And what you'll see when you do it is it's exactly the same as the two we've just done. And this is all you'll get on an exam. So if you can get your head around how this works, this question will be easy, because it's the same every time. Now what I'll do just to give you a guide is I'll go back to the previous one so you can sort of remember the steps. So you can see them if you need to. Any problem? Still got the +2, but ended up with -2x rather than -10x. Okay. Where you will have gone wrong is in the expansion. I'm just about to guarantee it. Have you put the minus across all of the terms in the second half? Amelia, these things always look weird. Try doing it with a cubic, you end up with junk all over your page. It's very easy to get lost. And it cancels out nicely. Okay, here's my solution. Compare what you've got with what I got. Can you see where you went wrong? That's if you went wrong. Good. Good. Yep, didn't. Oh, yeah. Okay. So you dropped a term. Good. Now, what I want you to notice is these questions, like nobody does the derivative by first principles in practice because it's a completely pointless exercise, as you'll see in a short while. Like to do something like get the derivative of minus 5x squared plus 2x, you do it in one line. You just write the answer down because you know what it's going to be. Because there are rules that you're allowed to use, able to use to do it. The thing is though, for a maths exam, a question like this means you've got to work with function notation there. You've got to be able to take x plus h and stick it in and work with that aspect of functions. You've got to expand, you've got to do expansions there and there. It puts a negative across a bracket, which is a common mistake that people make. And then you've got to do all this expansion and simplification. You factorise down here at the end, and then you do a limit problem. So one of these problems brings together in the same place a whole heap of the mathematics that you need to know up to this point. That's why they get put in exams. Now, the aim of the exercise is not necessarily to get it right. Take Reese's for argument's sake. His mistake was there, when he multiplied that bracket out, got minus 5x squared and the minus 5h squared was fine, but he forgot to multiply that by minus 5. So rather than getting minus 10xh there, he got plus 2, or minus 2. I multiply the first and third by minus 5. Good. It was the middle term that got missed, that one there. If you make a mistake like this in an exam, you might lose a half a mark. And depending on how things have been going, you might not even lose any. Because it's just, because you obviously know how to do that particular technique, but you just made a stupid mistake on one of the terms, it's not a big deal. So when you're doing these, if you get to this point here and you get stuck and things won't cancel out properly, what I've done, what I've seen done, is people will then write it in a form at the next line where it does cancel out so they can take the H out and then they just keep going anyway. Because in an exam, when you've only got a couple of hours and you're limited for time, this can be a fairly time-consuming problem, and it's hard, if you make a mistake in the middle of all of this text, it's hard to find where it is. So don't get too hung up at any one point with trying to get to the next step if you've made a blue somewhere. Just write it at the next line, put a note there to say, made a stupid mistake, I'll fix it up later, and then just continue on, make it look right, get an answer that you know is the right answer, and then move on. So that's how you do the derivative from first principles. In the exam, they will not be any harder than that, the end of semester exam, because otherwise it takes too long just to do the expansions and the simplification. So if you can do that sort of a problem, that's covered for the exam. Now, let's look at how you get the derivative easily. Let's do the power rule. This is the easiest one. Actually, not quite, but it's close enough to the easiest one. When you get the derivative, if you have a polynomial term like that one, 5x cubed, if you want to get the derivative of it, it's very easy to do it. The rule is, number one, you take the coefficient of x, which in this case is 3. You take it down to the front, down there, and you multiply the existing coefficient by it. The existing coefficient is 5. So the derivative, the front of it, will be 5 times 3. Having done that, you then, let's get rid of that, the second step is you take the existing coefficient, which is 3, and you reduce it by 1. So what this will become is the front becomes 3 times 5, which is 15, and the power part, the x cubed, becomes x to the 3 minus 1, reduce it by 1, which is 3 minus 1 is 2. So that's how you do it. That's all there is to it. Now, you don't have to do it in 2 steps. That step there is just showing you where the answer came from. So when you do it, you go straight from there down to there. Bring the number down the front, the existing coefficient down the front, and multiply. 5 3s are 15. Reduce it by 1, 3 down to 2. Now, if we go back a bit, we go back to the previous example, this one here, and I say get the derivative of that. What you actually know the derivative to be now is you grab the existing coefficient, take it down the front, and multiply it. 2 5s are 10, so it's minus 10. Reduce the coefficient by 1. It's currently 2, so it reduces down to 1 plus. Now, when you have a term like 2x, the existing coefficient is 1. Take the 1 down the front and multiply. Doesn't do anything, so it doesn't change the number. So that's still 2. X then becomes, you take the coefficient that's there and reduce it by 1. The existing coefficient is 1, so if I reduce it by 1, it becomes 0. But x to the 0 is in fact 1. So that term just disappears. So anything like this, which just has an x on the end, the x basically just disappears. So the derivative of 2x is 2. The derivative of 10x is 10. The derivative of minus 5x is minus 5. So anything with just an x on the end, the x just disappears. If you have something which has a higher power of x, what you do is you take the index down the front and multiply, reduce the index by 1. That's as simple as it is. So, the derivative of 5x cubed, therefore, is 15x squared. Let's have a look at this one. What I want you to do for me is to write down, we'll do it term by term, write down for me the derivative of only the first term. Don't worry about the rest of it, just what's the derivative using the power rule of minus 8x to the 4th? Minus 32x cubed. Got other takers? Good, good. So that's what it is. That term, I'll go back again, I won't jump the gun. That term is minus 32x cubed. Now write down that one. What's the derivative of 2x cubed? (6x squared). Good. Now do the derivative of that one. (2x). Good. Now what do you do with that one? What's good? It's 0. It just disappears. If you have something like 5x, something with an x on it, the derivative of that is 5. The x just disappears. If you have a constant on the end, and it doesn't matter what the constant is, like 25 or whatever, the derivative of 25, you just cancel out because it's 0. So, what you've written down is each of the parts. There is another rule which says that the answer would therefore, the derivative of this would be minus 32x cubed plus 6x squared plus 2x. You just do each of the terms separately, and the sign at the front doesn't change in this one. Right? Now, we notice that the signs there, we've applied the power rule. The number we were bringing down in each case was positive. So that means that didn't influence what the sign at the front was going to be. So the signs in the answers, there, and there, are exactly the same as the original problem. Now, putting it technically, there is actually another rule for this, but we don't usually learn it as a rule. If you have a function which is the sum or subtraction of a group of functions, like it's function plus function plus function minus function minus function, the derivative of the whole thing is the same as the derivative of the individuals were using the same plus or minus between them. Right, so that's a rule as well, but we don't really learn it as a rule because it's trivial. Now, what I want to do, that's basically it, all I expected to get to tonight, and that's essentially the hour up. What I want to do is to finish off with one problem which illustrates the use of, hang on a second, I'm trying to enter text on the page, there we go. What I want you to do is if I have f of x equals x, I can't do a thing, to the negative 3, right, x to the minus 3. What I want you to think about, just for a second, is what would be the derivative of that? We know that x, if x to the minus 3, whoop, hang on a second. X to the minus 3 is actually the same as 1 over x cubed. So that's what minus 3 actually means. What would be the derivative of x to the minus 3? If it was x to the 3, the derivative of x to the 3 would be 3x squared, because the 3 comes down and the index then gets reduced from 3 to 2. But what if it's x to the minus 3? What would happen then? One-third x to the 2? Sort of close, but not quite. What I want you to do, the answer to this is done in exactly the same way as the original problem. If I write this as, get my pen back. If I write it as x to the minus 3, and I say it to myself exactly the same way as I did it before, you'll get what Cale got. What you do is you take the existing index down to the front. The existing index is negative 3. So you go down to the front and multiply. So that then gives you a front. Because the existing index doesn't have anything there, we consider it to be 1. So the new front, the new coefficient becomes minus 3. The index, I have to take the minus 3 and reduce it by 1. So that becomes minus 4. If it had been 2x to the minus 3, well, that didn't work. That's weird. 2x to the minus 3, the derivative of that would be, you bring the minus 3 down the front and multiply, it becomes 2 times minus 3 is negative 6, x, reduce the index by 1, minus 4. Is everyone happy how that works? Cool? Yep. Good. If I was a betting man, which I'm not, but I would bet every cent I had that in the final exam you're going to get something like f of x, you can never do x's, if you do it too fast it has a heart attack, equals 3 over x to the 4th. You're going to get something like that. So that it's going to require you, the first step when you get this is you rewrite it as f of x equals 3x to the minus 4. That's the first thing you do, and then you get the derivative of it. So the derivative in this case, f dash x, would be, you grab the index, bring it down the front and multiply. So minus 4 comes down the front and times it by 3. So that would be minus 12. X is currently minus 4 as an index. Reduce it by 1, becomes minus 5. And you could then, if you wanted to, write that as minus 12 over x to the 5th. So that's essentially as far as I wanted to go tonight. To go on any further would require us to now look at the chain rule. which is the very next technique for differentiation that you have to know. And I think if we did that, we'll have probably gone one step too far. Now, before we finish, has anyone got any questions about anything you've seen tonight or anything else that we've done up to this point that you'd like to raise? Good. That last function, yep. D over dx, etc. Oh, sorry about that. You know, probably that's what happens when you've done this stuff a lot. You do things without thinking about it. A very simple answer. It looks scary, but it's not really. What we've been doing up till now is if I have a function and I've called it f of x, if I get the derivative of it, the way I've been representing it is the f dash. That thing there tells me it's the derivative of the f of x. When this was originally done, it was done by, as I've said, it was done by Newton and by a fellow named Leibniz. Newton was a British and Leibniz was a German, and they developed this idea of differentiation separately, completely independently, but roughly at about the same time. What happened was that the way they wrote it when they were talking about it was slightly different. One of them used this sort of notation, this dash notation. The dash meant that it was the derivative. The other one used if I have my function is f of x, if he wanted to talk about the derivative, he talked about that, df dx. It's exactly the same thing. Df dx and f dash x are exactly the same thing, and you can use them interchangeably. Anywhere in mathematics, both notations are equally acceptable. What you find is that sometimes one notation is easier to use or explain or work with to explain what you're doing than the other notation. Most of the time when you're working in fairly simple situations, the dash is what people use. But when you're starting to do things like look at some of the applications of the chain rule or the product rule, these sorts of things, some people prefer to use the ddx bit. What this means here, that bit there, that ddx of gx plus h of x minus m of x, what that means is ddx means get the derivative of everything. So it's no scarier than the other one, it just looks a bit different. Does that sort of make sense? I think so, okay. At this stage, for the next few days, pick the one you like, which is probably most people use the dash one when they're first starting with this. Use that and just stick with that. When we do our session next week and we start looking at the chain rule, we're actually going to be using the ddx type of way of representing the derivative, because it makes it easier to understand what it is you're actually doing with what's in the chain rule. But up till then, just keep doing the dash and it'll be fine. Has anyone got anything else they would like to bring up? Nobody? Okay, well that's basically it for tonight, folks. Thanks for your time again. I appreciate your input. It certainly makes it a bit better when we've got people to talk to. And I'll see you next week. Don't hesitate to give me a yell if you need anything about any of this. Night, Reece. See you, Amelia. Joshua, Kale. Good night. Thank you.